How to Keep Your Balance is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video, How to Keep Your Balance, discusses systems in chemical and thermal principles and defines the general balance equation. The companion video, Speed Balancing, gives additional definitions, hints, and suggestions on how to quickly and correctly solve your balance equations for your systems. What is a system? In chemical and thermal processes, systems and processes are used interchangeably. A system or process is a collection of inputs, outputs, and transformations. It can be an individual unit process, such as a chemical reactor, or a distillation column, or a collection of unit processes, like an oil refinery or a chemical processing plant. It can include more abstract ideas like a transportation system or a municipal sewage system. We can have a hierarchy of systems, with overall systems consisting of groups of individual systems and subsystems. We model the system or process with sets of equations that typically fall into two classes: conservation laws or balance equations, and constitutive equations. In this video, we are focusing on conservation laws or balance equations. What are the steps to working with a system? First, define your system type and boundaries. In the taxonomy of systems, there are several classes. The first of these is transient or steady state. In a transient system, the values of process variables such as temperature, pressure, or composition are changing with time. In a steady state system, the values of process variables do not change with time, but may change with position, what electrical engineers call a DC steady state. For example, in a heater, the temperature of a fluid passing through it changes from the inlet to the outlet, but if you measure the inlet temperature versus time, you find it doesn't change, and if you measure the outlet temperature versus time, you find that it also doesn't change. To reach steady state, most systems have to go through a startup or transient period. Next is how mass crosses the boundary of the system. In a batch or closed system, you supply the system with a batch of materials before the processing starts, then close the system so no mass crosses the boundary, and begin the process. When the process is complete, you open the system and remove the batch of processed contents. During the time the system is closed and processing, it is called a closed system. Batch systems are usually also transient systems, since steady-state batch systems are really boring because no process variables like temperature, pressure, phase, or composition are changing. Essentially, nothing happens. In a continuous or open system, mass is continually crossing system boundaries, like in a tankless hot water heater, while you have a hot water faucet turned on. Open systems can be transient or steady state, but the goal is usually to reach steady state and remain there. For example, in a system consisting of a shower head, a valve, the piping, and a tankless hot water heater, when you turn on the shower, the system is transient. It takes time for the water to start flowing, time for the tankless hot water heater to turn on, and time for the water to start heating. However, if you wait long enough, the flow rate of water is constant, and the temperature of the heated water leaving the heater is constant, so it is a steady-state system. The majority of systems in chemical processing are continuous systems. A system where mass enters but doesn't exit, or exits but doesn't enter during processing is sometimes called a semi-batch system. They are not nearly as common as continuous or batch systems, but they do exist. For example, a pot of water boiling on a stove where the water is evaporating, or a fermenter which produces and vents carbon dioxide. Here we present a set of examples of systems or processes with their classifications. First, a filling bathtub with water running in and out. It is an open transient system. Open because mass is crossing the boundary, transient because the amount of water in the tub is changing with time. Next, a partially filled bathtub where the flow in equals the flow out. It is an open steady-state system. Open because the water is running in and out. Steady state because the amount of water in the bathtub is not changing. Third, a filling bathtub with the drain closed. It is a semi-batch transient system. Semi-batch because water is entering but not exiting the tub. Transient because the amount of water in the tub is changing with time. Fourth, a bathtub full of hot water that is cooling. It is a closed transient system. Closed because no water is entering or exiting. Transient because the water temperature is changing with time. Lastly, a bathtub full of room temperature water. It is a closed steady-state system. Closed because no water is entering or exiting the system. Steady state because no system variable is changing with time. Three final subclassifications are control volume, insulated, and isolated. A control volume is an open system, whether transient or steady state, where the system boundary has a fixed volume and shape. An insulated system is one in which no thermal energy or heat is allowed to cross the system boundary. An isolated system is one in which nothing crosses the boundary, neither mass nor energy. The general balance equation. All entities which can enter or exit a system are subject to the general balance equation, which reads, the input plus the generation equals the output plus the consumption plus the accumulation. The words have their standard meanings. Input is what goes into a system, generation is what is generated within the system, output is what comes out of the system, consumption is what is consumed within the system, and accumulation is what is accumulated within the system. The rest of the videos on the website are arranged roughly in terms of what the general balance equation is applied to. First are material balances, or mass and mole balances. A mass balance is sometimes called the conservation of mass, so it is a conservation law. We will not do relativistic balances, so mass is conserved. Next are energy balances, also called the first law of thermodynamics. Again, without relativistic effects or ultra-precise measurements, energy is conserved, so the first law is a conservation law. Then come entropy balances, also known as the second law of thermodynamics. Entropy is not conserved, so the second law is not a conservation law. Finally come exergy balances. Exergy is not a conserved quantity, so an exergy balance is not a conservation law. Exergy finds its greatest use in maximizing process energy efficiency. For conserved quantities, like energy, mass, and atoms, the generation and consumption terms are zero. For steady-state systems, the accumulation is zero. For writing the balance equations for a system, there are two types of balances, differential and integral. In differential balances, all terms in the balance are rate terms, for example, moles per second, gallons per hour, picograms per year. They are usually written for a particular instant in time. For transient systems, differential balances are differential equations and usually need to be integrated to find the required solution. Differential balances are usually used for continuous processes. In integral balances, all terms in the balances are amounts, for example, moles, gallons, and picograms. They are usually written as the difference between two times. They are usually used for batch processes. When writing balance equations, we need to distinguish between intensive and extensive properties. An intensive property of a substance is one that does not depend on the mass or moles of a substance, such as temperature, pressure, density, or composition. An extensive property of a substance is one that does depend on the mass or moles of a substance, such as volume or weight. It is quite frequently useful to define an intensive property that is related to an extensive property. These intensive properties are specific, or molar, for properties, and are usually indicated by a circumflex, for example, specific volume. As mentioned, the next video, speed balancing, gives additional definitions, hints, and suggestions on how to quickly and correctly solve your balance equations for your systems. The takeaways are, 1. Always define your system. You need to decide if it is open, closed, or semi-batch, if it is transient or steady state, if it is a control volume or not, if it is insulated or not, and if it is isolated or not. 2. You need your balance equation, or equations, for mass or moles, for energy, for entropy, and/or for exergy. 3. Determine if you need a differential balance or an integral balance. 4. For conserved quantities, the consumption and generation terms are 0. 5. For steady-state systems, the accumulation term is 0. Thanks for watching. This video was brought to you by the DOFPro team. How to Keep Your Balance, Just the Facts is an episode of the Degrees of Freedom Project. Just the Facts videos on chemical and thermal principles. If you want the full story version with an in-depth discussion, use the link in the description. Definitions and additional details can be found in the webpage link in the description as well.